Hello and welcome to this film, which again is about electrochemical cells, but deals with some everyday examples of cells, which most people, I suppose, would call batteries. Now, it's important to realise at the outset of this film that you don't have to be able to remember the details of these cells, but when you're given the details of the cells, you do have to be able to remember how to predict what's going on in the cell. So in other words, this film's really about practicing the principles that we covered in the previous film. It gives you a bit of background, it gives you a bit more of a feel about how we actually make real-life batteries. Okay, but it's not important to remember the details of the batteries, but it is important to be able to explain how they work. So let's see what we mean by looking at a really old-fashioned cell called the Daniell cell, named after a guy whose surname was Daniell. Okay, now Daniell combined the zinc and copper half cells in quite an ingenious way. He took a copper vessel, which he filled with copper sulfate solution. So he's got a copper half cell there. And he combined that with a zinc half cell by putting a zinc rod in a solution of sulfuric acid, which would dissolve some of the zinc and create zinc ions here. And he put that in a porous cup, which he then placed in the solution of the copper sulfate. We'll see why he did it this way in just a moment, but let's just look up the two half equations for the two half cells on our data sheet. Here they are. Okay, what can we tell from these two half equations? Well, we can tell, because the zinc is more negative, that the zinc is going to be the negative electrode. We can see that on our diagram there, and the copper is going to be the positive electrode. We can also tell that, I suppose using our clockwise rule if we want, that copper isn't going to turn into copper 2 plus and zinc 2 plus into zinc, because that would be anti-clockwise. So copper 2 plus is going to turn into copper and zinc's going to turn into zinc 2 plus, right? So once we've decided that, we can decide which one's being reduced and which one's being oxidized. In fact, zinc is giving up its electrons, so it's being oxidized. And copper is gaining electrons, so it's being reduced. Reduction always happens at the cathode. So this is our cathode, and oxidation always happens at the anode. So there's our anode, right? So what's going on? Well, there's lots of electrons on our zinc electrode, because this equilibrium is going that way. There's not quite so many on the copper one. So it is still producing electrons, just not as many. Okay, now these electrons are going to flow from the zinc round to the copper. And in fact, we could measure what potential difference there is between those two electrons between those two electrodes by adding a voltmeter. And now we've got an external circuit. We don't need a voltmeter to have an external circuit, but we do have an external circuit now. And the electrons are going to flow through that external circuit from the anode round to the cathode, as always. Okay, now then, what else do we know? Well, we know we've got a salt bridge here, right? That was the really ingenious thing about this device, was that he used this porous cup which allowed the passage of ions. Now electrons are going around there, so the negative must continue to go that way, so the negative ions are flowing through our porous cup in that direction, and positive ions are flowing through our porous cup in that direction. What else can we decide? Well, what else have we covered in the previous films? We can calculate the cell potential. Okay, now the cell potential, that's just the standard reduction potential of the reduction process minus the standard reduction potential of the oxidation process. Now, this was just one of the methods we used earlier to predict reaction feasibility. You can see here it's actually useful also for determining a cell potential. Okay, so let's do this anyway. We've got 0.3 minus 0.76, and that equals 1.06 volts. Okay, so by using the half equations from my data sheet, not only can I decide what's going to be going on in terms of reduction and oxidation and anode and cathode and electron flow and ion flow, I can also decide what voltage I'd get from a cell like this one. Okay, so that's all I've done there is I've just used some of the principles covered in the previous film, and that's all I'm going to do in the rest of these electrochemical cells. Okay, now, just like the previous cell, you don't need to remember the details of this cell, okay? We're being given the information about it in a slightly different way this time, okay? We're being told that zinc is the negative electrode. I can look up the zinc half equation on my data sheet, okay? And I'll see that it looks like that. And I can even look up the voltage, which is minus 0.76 volts. Okay? It's the negative electrode which tells me that the zinc is giving up electrons. Okay? It's being oxidized. Okay, so this is my oxidation. So my zinc negative electrode, the negative terminal, right? This is my anode. And there's lots of electrons there. So if I connected that to an external circuit, maybe it was a voltmeter, maybe it's an Energizer bunny or something, I don't know, then the electrons are going to flow from that negative electrode round to the positive electrode, which we can see in this case is actually made of carbon. And the half cell reaction that's going on inside here involves MnO2 turning into Mn2O3. Now, I don't know what the half equation for that is, and it's not on my data sheet, but I could be asked to write it. Now, you might think, well, if it's not on my data sheet, how am I going to know what it is? Cast your mind back a little bit and remember that you ought to be able to write half equations, balanced half equations for redox reactions, right? And here, I've got 2 manganeses here, so I'm going to need 2 there. I've got 4 oxygens here, so I need 4 oxygens there, so I add some water. And now I need to add 2 H plus ions here and 2 electrons. Now, this is reduction. It's gaining electrons, so this must be my reduction process, and my carbon electrode is going to be my cathode. In fact, you could say that this reaction, this half cell in here, is going to be the cathode. Where's my salt bridge? Well, the salt bridge is this paper soaked in ammonium chloride solution, which is separating this chemical paste, which contains my manganese dioxide, separates it from the metal case, but allows ions in the ammonium chloride to flow and to complete my circuit. Okay? Now, because this half equation isn't on my data sheet, I don't know what its potential is. But if I was told what the potential of this dry cell was, let's just imagine that it was 1.5 volts, then my cell potential, which is 1.5 volts, equals the E red, which is this one, right, minus 0.76 volts, right, because that was my E ox. So E red must be 1.5 plus minus 0.76 volts, which equals E red. That's going to be 0.74 volts. So in other words, I ought to be able to decide what the potential or the standard reduction potential is for my other half cell based on the fact that I know the cell potential and I know one of the 2 standard reduction potentials. Okay? So again, don't need to know the details, but I'm just using principles that I've covered before to decide what's going on here. I could even decide on the ion flow through this paper if I want. Okay? Right. Moving on. This is the lead acid accumulator, or what most people would call a car battery. Okay? Now, the half equations for this cell are on your data sheet. Okay? You don't need to remember them, right? But I suppose it's useful to remember what they are. Okay? If you're given details of a lead acid accumulator which has lead and lead oxide and sulfuric acid, then you can decide that you've got lead oxide and lead with sulfate ions, H plus ions in this case, and they are able to take part in these 2 half reactions. Notice something slightly odd here, right? I've actually written the electrons on the right of this one, even though on our data sheet, if I can just find it quickly, where are we, minus 0.36 volts? Even though this voltage is given for the reduction process as usual. Okay, so I've got lead oxide and lead both turning into lead sulfate. Okay, this is the reduction here, because we've got a gain of electrons. This is lead turning into lead ions and giving up electrons, so this is my oxidation. So this is happening at the anode, this is happening at the cathode. Once I've done this, I can find my cell potential, because that's E equals the E red minus E ox, which is 1.69 minus 0.36, which equals 2.05 volts. Now you might be thinking, but my car battery is 12 volts. And yes, you're quite right, because there's 6 of these half cell arrangements inside your battery. And in fact, that's why it's called a battery and not a cell. It's got a number of different cells. Okay, put 6 of them together, you get about 12 volts. When you're recharging, you have to put 12 volts into your battery, and that's what your alternator does in your car. It just reverses these two processes and gives you the reverse reactions, right? So we've got two lead sulfates there and there, and 2 waters there, turning into lead oxide and lead and 2 sulfate ions and 4H plus. Okay, so in actual fact, in your car, the discharge is constantly occurring, and so is the recharge. That's what your alternator does. Basically, it swaps between discharge and recharge all the time. Okay, but it's important to realize that if you're given the details of a lead acid accumulator, you can look up the half equations on the data sheet. You can calculate the potential of one of these cells in the battery, and you could actually reverse these two reactions when you recharge your battery. Okay, last one we're going to look at is called the hydrogen fuel cell, and compared to all the other ones, it's a much more modern electrochemical cell technology. Here's a diagram of one, but again, you don't need to remember the details. Let's just see what information we can get about our cell from the information that we're given. Hydrogen is at the anode, that means oxidation is taking place. Okay, so that means that 2H plus and 2 electrons, this equilibrium here, turning into H2, that's at 0 volts, that's our standard hydrogen electrode, that must be going that way, right? Because we're oxidizing hydrogen. Oxygen is turning into water, okay? That means that oxygen, if this was our oxidation, then oxygen must be being reduced. So let's look on our data sheet again for oxygen turning into water, but involving a gain of some electrons. Well, I can do that, okay, and I'll find it at 1.23 volts. I'll find that oxygen plus, where are we? 4H plus 4 electrons is going to turn into 2H2O. And that's 1.23 volts. Lost the ability to write there for a moment. So 1.23 volts. Now, again, cell potential, E red minus E ox, well, that's just 1.23 volts. So I can generate a voltage of 1.23 volts with a hydrogen fuel cell. Which is my anode? Which is my cathode? Well, reduction is always at the cathode. So my oxygen here is the cathode. Okay, and my hydrogen is the anode. Which way are the electrons going to flow? Through the external circuit. Well, they're building up on the hydrogen electrode because it's giving them up, and they're being taken by the oxygen. So the direction of electron flow through my electrochemical circuit, through my external circuit, is from the anode to the cathode, as usual. And here, guess what we've got? We've got a salt bridge, which is allowing the passage of ions, right? Our negatives are going that way, so negatives must be going that way. Protons, or H plus ions, are going through here, and they're reacting with the oxygen. Look at that. Look how ingenious that is. Okay? And we're producing water. as our only product of this reaction, which is why people love fuel cells, because we're not producing any harmful byproducts. Okay, so hopefully that's a bit of practice at the principles of electrochemical cells that we covered in the last film. As usual, if I've made any howlers or if you've got any questions to ask, comments would be very much appreciated. So would your questions if you want to come and ask them. But please try and make sure that you understand before you move on.